Hello friends. So today we will be discussing thermal stresses and strains. Basically the stress induced due to the temperature change in the material. So that we will be discussing today and we'll be solving some of the examples. Let's proceed with the lecture. So regarding thermal stress and strain, thermal pertains to the temperature. So we are focusing here on temperature change in the material. So change in the temperature can result in the change of the dimensions of the material. Then the material expands corresponding to the increase in temperature and may contract if there is decrease in the temperature. And it has been observed that generally there is a linear relation between the dimension change and the temperature. In majority of the cases it has been observed. Some of the very basic assumptions which we must consider while dealing with thermal stresses and assumptions are the material is homogeneous and isotropic. So I will straight away come to the formula or equation which generally is being used in case of thermal stresses. Or basically when there is a temperature change, we say that thermal stress is induced in the material because of certain restrictions, and we are concerned about more concerned about the change in the dimension. So we will just discuss a relation, that is change in the length, so which is given by the product of alpha and change in temperature and length, initial length of the body. Now alpha is the linear coefficient of thermal expansion. So if we have a list of materials, for every material, generally for all the materials, we have the value of this thermal expansion coefficient, from where we can know that which material has a tendency to elongate more. And the SI unit of this coefficient is per degree Celsius or per degree Kelvin. So now, in case if there is a variation in the temperature along the length of the subject, so then the same change in length can be expressed in the form of integral. So since alpha is a constant, so it cannot be integrated. So we have this expression. We will integrate the change. We will select an element of length dx, and then we'll integrate product of product of delta t and dx. That is for those members which are subjected to the variation in temperature along their length. So let's come to thermal stresses. Now stress basically means resistance. The resistance offered by the material when some sort of a external loading is applied on it. So what about thermal stresses? Let's see, there is a bar of length L which is at certain temperature. Let it be at room temperature. For example, if it is if the temperature is raised, let it be to some T degree Celsius, so what will happen? It will elongate. So I have shown it on one of the sides. It may elongate on both of sides also. It depends. So this is just to explain. So because of the change in temperature, it will elongate. Now, if it has elongated, there is no stress because it has released. The thermal load has increased the length. But if you restrict this change in length, so then material will resist, and stress will develop in the material. For example, if I take two fixed supports, and place this bar within these supports, now on the with the when it is subjected to the same temperature change to which this bar was subjected, so what will happen? Where this change in length will go? So this change in length will be restricted by the supports. In turn, some compressive force will act upon this. Say this is a compressive force. This will act, which will try to push it back. So let it be on both sides. So that is how the equilibrium is maintained. So the thermal extension is countered by the mechanical extension or the mechanical loading. So that is how thermal stresses are induced within the material. So constraining of the displacement results in thermal stresses. So let's move ahead. Let's take an example. So this is a bar of length 1.2 meters. Now this bar has been supported by rigid supports from both the ends. The cross section of the bar is circular of 12 mm diameter. And let's see what else is given to us. So this is the situation. The fitting of the steel bar. So the material of the bar is steel. So it is ductile. It means there will be a extension. So the fitting of the bar within the rigid supports is carried out at 25 degrees Celsius. So this is the initial temperature. So let it be a room temperature. So if the temperature of the bar is increased to 100 degrees Celsius, so means uh, there is a temperature change of 80 degrees Celsius. So what would be the average normal stress developed in the bar? Neglect weight of the bar. So this is the question. So when we talk of average normal stress, the average normal stress, the basic formula for this normal stress is the axial load divided by cross sectional area. Now you will think this is the formula for mechanical loading. Yes, this formula we had already used for axial loads. So it means because of thermal stresses, uh, we get some mechanical loading also. So it has already been explained in the previous slide, but I will again explain in the same problem. So let's start with the problem first. So this is the bar now. So this is the mechanical load. So how this load has come up? How this P on both sides? As I have told you that because of this rigid supports, the extension of this, say this is the extension of this, which would have been there if it was free of supports. This extension is being restricted. So how it is being restricted? Because of these supports. It means some mechanical load is acting at this junction, acting at the junction between the rigid support and this bar, which is pushing it back. Now this is a mechanical load. So in essence, we can say the restriction gives rise to a mechanical loading. Now, as it has been shown here, the thermal displacement will be pushed back by force P so that the bar restores its initial position, and the net displacement becomes zero within the rigid supports. Now what is that net displacement? It means the thermal displacement or the change in length because of the thermal load equals to the change in length because of the mechanical load. See, we have to frame a mathematical equation, and that's the best suited equation here. The change in length due to thermal load is countered by the change in length due to the mechanical load. So we get this equation for the change in length. So let's see. This is the bar with the load as I had explained. Now the net displacement is zero because of the rigid supports. Now, so we have substituted the formulas for thermal expansion. We have the alpha and then change in temperature and length, and for mechanical displacement we have PL upon A. Now, at this point of time, we need the value of alpha and E. The alpha and E are the values of material. This alpha, coefficient of expansion, and E, modulus of elasticity or Young's modulus. These are the values of material. So our material is steel. So these values are already available from the literature. We can take these values because the researchers have done a lot of experiments and devised these values for different materials. I will just try to show you here. As an example, I have taken some of the materials with the value of their thermal expansion coefficients. You can see aluminium, copper, brass, gold, steel, glass. So from here we can see the expansion coefficient is in the decreasing order. It means aluminium expands more if compared with the other rest of the materials, and glass is having the least thermal expansion coefficient. So there is an extensive list. So we can use these values and in our wherever they are desired. Now, one thing I would like to stress upon here is the benefit. Benefit means, suppose this is a, I've taken a bar. Let's suppose this is of this is made of aluminium. Let's suppose it is a machine component. There is some component which is being used. It's made of aluminium. Now, since aluminium has is more prone to the extension, it will extend more. So that extension is not desirable because of certain reasons. Let's not discuss those reasons now, since we are not into design. So I just wanted to restrict that extension, that change in length. That's what I want, and I don't want to replace this aluminum material because it will incur cost. So what I can do, depending upon the calculation, the requirement, so I can add. Let's suppose if I develop a composite material and I use steel with aluminium. So what will happen? The expansion coefficient of steel is 12. Its coefficient is 12, and the coefficient of aluminium is 25. So what do you think about it? What will happen here? Yes, the steel will restrict the expansion of aluminium because of its less thermal expansion coefficient, and we can come to an equilibrium state. So this is just to give you an idea that we do develop develop composites with different expansion coefficients. Again, we have to make certain calculations so that we come to the exact value. So that is sort of a practical significance of these coefficients. Okay, coming back to the problem. So what we have to find now, we have to find the value of P. So rest every value is known to us. There is only one unknown, that is P. So let's substitute all the values, and here we get 20.4 kilonewton. So this is the load acting on this. This is a P, load acting on the cross section. Now what would be the average normal stress? Simply the P divided by the cross sectional area, and we know what the cross sectional area, the diameter is 12 millimeters. So pi d square by 4 is the area. So this is the 180 megapascal. So that is how we make use of this the formula related to the thermal stress, thermal strains or stresses. Let's discuss one more example for more clarity. Now here there is we have taken a cylinder of some material that we'll discuss what is the material. This cylinder is being placed within the two rigid supports as shown. Now how to maintain this practically? We have used two bolts. Now you know what is a nut and bolt. So we have used two bolts. This green part is the nut. These are the nuts for tightening these bolts. So and when you tight, you can say the bolt is like this. There will be some part. More you tight, more it will extend. So what I'm showing is not the displacement, it's just the length of the bolt. So now this is the case. Let's say what is given to us and what we have to find out. Let's see. Lengths are given to us. Length of the bolt 150 millimeter. So length of the cylinder is 150 mm and length of the bolt is 200 millimeters. What is given to us? So diameter of the cylinder is 40 millimeters and material of the cylinder is copper. Now I had already shown you the expansion coefficients of different material, and you have seen the copper also. I think it was next to aluminium. So what about bolt now? So diameter of bolt is 8 millimeters and the material is of steel. Now again the combination they have sought out, copper with steel. So we are not focusing on that combination, how they have come to this material steel. So here we are learning how to make use of these formulas. So that is our main objective. What else given to us? So he says the cylinder was placed within the rigid supports at 20 degrees Celsius. Okay. So what is to be found out is the force acting on the cylinder when temperature has risen to 100 degrees Celsius. Now I think this is quite clear to you that the thermal expansion of the cylinder is being restricted because of the rigid supports. Rather, I will say because of the supports due to the placement of bolts, because if there are no bolts, practically you cannot hold the supports. That's quite clear to us. So we have to find the force induced. Now, can you guess what force will be induced? Yes, because if it is free, the cylinder is free of supports, it will expand. So that expansion is being restricted. So yes, we will get a force, compressive force on the cylinder. Okay, let's see. Let's move further. So let's find out the values of the materials. It means the expansion coefficient and the Young's modulus, which is very much required here. So again, from the literature, from the available literature, we have these values for copper. The coefficient, expansion coefficient is 17 into 10 to the power minus 6 per degree Celsius, and Young's modulus is 117 gigapascal. Now for steel, it is 12 and 190. So this is the combination with us. Now, due to the change in temperature, so that's 80 degrees Celsius, there will be extension in the cylinder if it was free of supports. So that we know. And that as an example, I will show you here. This blue part is shown just like, suppose it is a extension. Now this extension is being restricted because of these supports. So however, due to supports, there will be push exerted onto the supports and to the cylinder. So we are talking about this junction, the junction between the cylinder and the support. And the supports are able to resist. So as I was telling you, supports are able to do their work to resist because of the bolts. And in bolts, we always have tensile force. Bolts will be having tensile force because if you can recall, if you take a nut and bolt and tight the nut, what will happen? The bolt will extend more. So it means the bolt is having tensile force, or it will always have a tensile force. So that is how this balance is being maintained. Now what we can see here, it means the net deflection or deflection between within the supports of bolt and that of cylinder, it should be equal. They should have same net deflection. Okay, let's move ahead and see. Now I have taken finally the forces acting here. Now as it is clear, because there will be a push, so this mechanical force is required here to push it back, to push back the thermal displacement so that the equilibrium is maintained. It is being done by the supports. Now supports are able to do their work because of the tensile force acting in these bolts. Because if you tight the bolt, let's say as an example, if this is a bolt and this is a nut, if you tight the nut, what will happen? It will extend more. It will extend. The moment you tighten, more you tighten, more it will extend. So there will be tensile force in the bolt. So because of the placement symmetry, the bolts will have same force. Just for simplification, I have taken it P by 2, P by 2. It means the bolt will have a total force of P. Or we can solve it by taking P and P also. It hardly matters. I hope it is clear. The forces acting on the cylinder and that of the bolts are in front of us. Now we can move ahead. Due to the temperature rise, there will be thermal extension in cylinder, that we know, which will be opposed by the mechanically induced deflection caused by force F. So that's delta Cn. So never forget, in this case you have thermal as well as mechanical. They go hand in hand. So the total deflection in or net deflection in the cylinder will be because of delta Ct and delta Cn. What about bolt? In bolt there will be a mechanical extension, because I told you delta Bm due to P by 2 in addition to thermal extension delta Bt. Now exactly if you see, and this I will talk about cylinder. In cylinder there will be thermal extension, but if you talk about this mechanical, the change in length because of this mechanical load, it will be compression. The force F is compressing. So net deflection in the cylinder will be delta Ct minus delta C m. And when you talk about bolts, because bolt, there is a tension, there is a tensile force, and the net deflection will be the summation of these two, thermal extension and mechanical extension. I hope it is clear. So between the rigid supports, yes, net deflection in cylinder is equal to net deflection in the bolt. Now let's see what about this net deflection. In cylinder, it will be uh, the difference in the thermal and the mechanical extension. But in case of bolt, it will be summation. Since bolt length will extend more, it will go up and up. More you tighten. So this is the relation what we are having. Now we can substitute the formulas. We know the formulas for thermal alpha delta TL and for mechanical PL upon A. It's quite simple. Let's substitute the formulas. Now our objective is to find these forces P and F. So let's see how many unknowns are there. Now, this is one equation, and we are getting unknowns, two unknowns. The F is also unknown, P is also unknown. Well, let's see how to find them, because two unknowns mean we need two equations. You might have guessed. You might have guessed how to find out these two. And remember, the system is in equilibrium. That's very important. So for maintaining the system in equilibrium, we are doing all this. We have this arrangement with us. So these are the areas we have calculated. Let's substitute all the values. So this is a relation between the load on the cylinder and load on the bolt. Now, since the system is in equilibrium, we can apply equilibrium conditions. So we can sum up all the vertical forces equal to 0, and what we get, F is equal to P, because minus F plus P by 2, if you sum up, it becomes minus of F, let me write here, and plus P by 2. P by 2 plus P by 2 means P equals to 0, because the system is in equilibrium. So we get F is equal to P. Now from these two equations, we can substitute the value of F equals to P in equation first, and here you get the load acting on cylinder is 3.3 and load acting on the bolt is 1.65, or the total load P becomes almost equal. It becomes equal to 3.3 only. See, that is how we deal with the systems with the different materials. As I told you, you can join these materials also to develop a new composite. So just you have to, if you are practically designing something where there will be thermal stresses, you have to decide the materials intelligently, because the thermal strength and the mechanical strength, they both play a role. Again, it depends on it varies from application to application. So this is all from my side for this lecture. Hope to see you soon. Thank you very much for listening. Thanks.